So that last video had a lot. Let's just recapture a couple of things and then expand. So we introduced the idea of electrical potential energy, which is just like any other form of energy. And this is the capacity a charge, specifically, because you have to have charge, has to affect the environment due to, remember, we're talking about energy, that's a capacity to affect the environment. A potential energy is due to location, so specifically due to its location in an electric field. Okay, and then we said that the larger the quote-unquote falling distance, that meant more electrical potential energy. Then we introduced the notion of, I introduced the notion of just electrical potential. Electrical potential is not the same thing as an energy. It is not an energy. Remember, that's the description of a location in space. I'm not going to write all this out. I'll just write out the basic bit here. It's a description of the location in space that says how much electrical potential energy would be stored per unit charge at a location in space. Okay? So let me give you another analogy. I went to the supermarket before and I got 4 lemons for $3. 4 lemons for $3. Knowing that I had 4 lemons for $3, how many lemons do I have? You don't know. That's exactly what I mean by electrical potential. If I know that at a certain location in space that the electrical potential is 20 volts, I do not know how much energy anything has. But if a 1 coulomb of charge is placed there, that coulomb of charge will have 20 joules of electrical potential energy. If 4 coulombs of charge is placed at location in space, that will have 80 joules of potential energy, right? So that's a description of something, of the location in space that tells you how much energy you would have if you were to put charge at that location in space. And then we had the notion of potential difference. Actually, let's just do symbols here. EPE, V, and then delta V. Delta V was different than electrical potential, although obviously related, because this describes the location in space. This is the work done per charge to change position in an electric field, which is why delta V was work done per charge. And that work could be a change in electrical potential energy, or it could be change in kinetic energy, whatever is appropriate for the given context. Okay? And so those were the notions that we had before. So let's go on to a couple of other things on this. So let's say, just to give an example, between 2 points in space, there exists a potential difference of 50 volts. So between, say, position A and position B, there's a potential difference of 50 volts. How much work would be required to move from A to B for a 3 coulomb charge? Okay? So here's the thing. This is where it gets really kind of technical, and I'm going to tell you that there's a lot of technical stuff that we are not going to talk about. I know that there's a potential difference of 50 volts, but we said that potential is about something about that location in space. So I actually don't know what the potential at A and what the potential at B is. The potential difference is 50 though. Maybe A is at 100 volts and B is at 50 volts. Or maybe A is at, 0 volts and B is at negative 50 volts. Or maybe A is at, 20 volts and B is at 70 volts. I don't know. All I know is that there's a difference of 50 volts between those two. But let's see what that could mean. Let's say that this is actually what's true, right? So that means that there is a potential difference between these two things. So if I were to put a positive charge at position A, that's what this is, it would naturally want to go to position B, right? Because we said positive charges want to go from higher potentials to lower potentials. That would mean that there exists an electric field going from A to B, because we also said before that anywhere where there's a potential difference, actually we didn't say this, I'm going to say this now. Anywhere where there's a potential difference, there is an electric field between those 2 points. And we can verify that by looking at what we saw here, is that we had an electric field here and these points of potential difference. Notice that the electric field points towards lower potentials. That's why this is true here. Now, how much work would be required to move the charge from here to here? Well, here, if I put a charge at A, it would naturally go to B, and so it would be the electric field doing work here. Now, if the positive particle was at B and I wanted to go to position A, I would have to do work, not the field, to force it to A, because it wouldn't want to do that. That's not what these questions, we're going to focus on that. Because remember, when we talked about the concept of work in the past, let's revisit that. We defined work to be force, displacement, cosine of theta, where theta was the angle between the force and the displacement. That meant that that work could be positive or negative based on what that angle was, right? If I moved in this direction, but the force was in that direction, there was a 180-degree angle, this would come out negative. If I moved in this direction, the force was in this direction, was positive. Remember, positive work was a gain in energy. Negative work was a decrease in energy. We're not going to deal with that in all of this because that gets very complicated because of the signs of the charge. So we're just going to deal with magnitudes here. So the amount of work magnitude is going to be the magnitude of the charge times the magnitude of the difference in potential. Because, right, if I go from A to B, that is, because remember, delta is always final minus initial, that would actually be 50 minus 100, or a negative change in potential. But we're not going to get into that because that's going to get too complicated too quickly. When you choose to use signs in all of your charge equations, the whole thing becomes a lot more complicated and a lot more complicated beyond what we want to do for an intro course. So here we go. This is just going to be 3 coulombs and then the potential difference of 50 volts. In fact, I'm just going to use parentheses here because we're not going to plug in charges for anything, and that's going to be 150. Remember, a volt is a joule per coulomb, so joules. Now, let's see if I did the same problem, but I wanted to see what about for a negative 3 coulomb charge? Well, the negative 3 coulomb charge would undergo the same amount of work to move between those 2 positions in space. But let's just talk about what would happen naturally. A negative particle would naturally go from B to A. A positive particle would naturally go from A to B, right? If I wanted the positive particle to go from B to A, I would have to force it to go there, right? So let's think about that in terms of energy. A positive particle, I would increase its potential energy by going from here to here, since it wants to fall back in this position. But if I have a positive particle naturally doing what it wants to do, then it would be speeding up, right? The work being done here would change the kinetic energy. So that's the way we're going to think about it, right? If the thing does naturally what it would do, then we're talking about changes in kinetic energy. And if we're forcing it, generally we're talking about changes in the electrical potential energy of the object if we're going opposite the direction it would fall. Okay? So far, so good. Hopefully. Next, let's say I had that same two positions in space A and B, and I wanted to say an electron is moved from A to B, because naturally the electron would not want to go in that direction. So we know that this is the difference in potential between these 2 points is 50 volts. So what would that mean? Well, work would be QV, and we would put in a charge of 1.6 times 10 to the negative 19th coulombs times 50 volts, and we would get 80 times 10 to the negative 19th joules, which would be 8.0 times 10 to the negative 18th joules. That's a really, 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 really small amount of charge. So what do? Well, when we encounter really big or really small numbers, what we've done in the past is we've made new units. Remember when we were doing gravitation and we were talking about these massive distances, we started using something called the AU, the astronomical unit, because it was more convenient. Remember also that we had something that was called 1e, the elementary charge of 1.6 times 10 to the negative 19th coulombs, because it was easier to think of the charge on objects in terms of e's rather than these, this bizarre number. Well, we're going to define a new unit of energy here, one that makes our life a lot easier here. So watch what we can do. If I have one electron, that is going to be a charge of 1e, and negative 1e, but remember we're plugging in magnitudes, and we're moving that through a 50 volt potential difference. And so what we're going to do is we're going to create a new unit of energy. And here, what we're going to do is we're going to have 50, and then what's called an EV, or, and I know you've seen this before, an electron volt. An electron volt, or 1 EV, is the work needed to move one elementary charge through a potential difference of 1 volt. So that 1 EV is equal to 1.6 times 10 to the negative 19th joules. It's just a smaller unit of energy that is oftentimes more convenient to use for the scale of the measurements that we're doing here. So it is a unit of energy. All right, cool. So with that out of the way, we can now go back to the next thing. Let's go back to the parallel plate capacitor. So if I have a parallel plate capacitor, that would mean that one of the plates is charged positive, one charged negative, positive and negative. There we go. We said that the electric field in this region would be from here to here, and that electric field would be uniform, because that's why the parallel plate capacitor is pretty amazing. What I didn't talk about is, well, how does that parallel plate capacitor gain those charges like that? Well, this is actually what we're leading up to here. So, if I were to put a positive charge in here, where would it have the most amount of electrical potential energy? Hopefully you said here, because then it would have the largest falling distance down to the negative plate, right? That means that this positive plate is at a higher potential than the negative plate. So if I call this a V positive and V negative, right? That must mean in this region in space, there exists a difference in potential between the positive plate and the negative plate, okay? A difference in potential. Once again, anywhere where there's a difference in potential, you're going to have an electric field pointing towards from the higher potential to the lower potential. So what is creating that difference in potential? Well, what's creating that difference in potential is often a battery, because that's what a battery provides, is a difference in potential. So let's say I have a AA battery here, right? And a AA battery provides a difference in potential between the two ends of 1.51 volts, because something is happening in there, which we'll talk about the next unit that does that. So what's happening here is this section or plate is attached to the positive, what's called terminal of the battery, and this section is attached to the negative terminal of the battery. Boom. So there you go. And so that's what's causing this side to become negative and this side to become positive. It's not quite a charging by conduction, but it's a similar process, right? So what's happening here is that this thing is pulling electrons off this side and then forcing them over here. It's doing work on the electrons to push them there. So there you go. So I have a difference in potential between the plates. Now, here's the thing. In this region, I have a uniform electric field. So let's say we know then that the difference in potential here is the same as the difference in potential of the battery. But once again, that's just a difference in potential. Right, we know that this plate is higher in potential by 1.51 volts to this. That doesn't need to be 1.51 and 0, but let's pretend it is, even though it actually isn't, right? Okay, so there we go. Now, once again, it doesn't have to be 1.51 and 0, it just has to be a difference of 1.51. What do you think would be the potential at some point that's halfway between those two? Well, hopefully what you said is 0.7505, which is volts, which is half of the difference there. Well, why is it exactly half? Well, that's because this field is uniform. In the same way that if I had a ball that had 10 joules of energy, and I let it drop halfway down, it would have 5 joules of energy. The reason for that is because the potential energy due to gravity is, or has a linear relationship with the falling distance. Now, why is that true? That was true because the field, the gravitational field in this region is constant. Oh, since the electric field in this region is constant, it also has that linear relationship. Meaning then if I went like halfway then between these two, we would have we would have a potential that would be halfway between these. So what is that? Well, that is, I'm just gonna put in my calculator because my brain is just fried today. 1.13025 volts, right? And here, if I had that halfway, okay, that'd be half of that, or 0.375025 volts. Not pretty numbers, but there it is. But the important thing is, if this distance is x, then this distance is also x, and this distance is also x, and this distance is also x. I get the same difference in potential because the field is uniform. All right, so now what I want to do is link that to the last thing I want to talk about here. Potential gradient, or electric potential gradient. Electric potential gradient. What is this? The electric potential gradient. Remember from that previous idea, this is the notion that it is the ratio of the change in potential per unit position change. And remember, per unit position change is the same way as saying displacement. So therefore, that's the change in potential per unit displacement. And there we go. Now, in the last video, I made a link with the idea of potential gradient when we were talking about gravitation. The potential gradient here talks about, notice the potential gradient here would be a constant, right? Because every time I moved a certain amount, the potential changes by the exact same way when I move across the field. And that's because the field was uniform. Because, in fact, the potential gradient is the same thing as the electric field, right? Now, I'm going to put some magnitude signs around all this because, once again, we said we're just ignoring things with signs. We're just going to kind of use logic to deal with the signs. So the strength of the electric field is the same thing as the potential gradient. And that should make sense because if the field here is stronger, that means an object moving across there would experience a greater change in potential energy or a greater change in kinetic energy than with a weaker field, right? Because a weaker field would mean a weaker force. And if we think about the notion of work being force times displacement times the cosine of the angle, that means that if there was a weaker force, it would do less work over the same distance. It's the same concept here. So the electric potential gradient is the same thing as the electric field intensity. And this allows us then to do a lot because, remember, I said that the purpose of the parallel plate capacitor was to have a region of constant electric field that allows us to do experiments. This lets us know now how I can choose the electric field by choosing different batteries or by making this distance smaller or bigger. I can change the strength of the electric field in here so that I can do the sort of things I need to do to particles in this space. So this becomes the mechanism by which I can use the space inside of the parallel plate capacitor in order to do experiments. Okay, now I do want to just do a little sideline stuff before we talk in the next video about those experiments. Let's say I have a positive particle here, right? And so let's say I were to put another thing at this location, another positive charge here, right? What would happen to it? Well, we know that that positive particle would go away, right? It would experience a force, right? So since it would, quote unquote, fall away, it would have a certain amount of electrical potential energy. Where else could I put a charge such that it has the same amount of electrical potential energy as a charge that would be put there? Another way of saying is, what does the equipotential surface look like? Well, hopefully what you're thinking to yourself is that it would be something that looks like this. And it'd be very easy to say that that's a circle, but remember, this is an equipotential surface. It's a sphere around that. And this would have a certain potential. So let's call it, if that's point A, this says VA. So then if I have another equipotential surface, that is VB, right? And we'll call this position B. Okay, so where would a proton have the most electrical potential energy, A or B? Well, it would be the electrical potential energy of a proton at A would be greater than electrical potential at B, electrical potential energy B, because we know that no matter where I placed it, it would go outwards, and A would go outwards to infinity, B would go outwards to infinity, but A would have longer to fall, right? An electron in this space, if I were to place an electron at B or at A, where would have more electrical potential energy? At B, right, because it's going to fall inwards here. So the electrical potential energy at B would be different than the electrical potential energy at A, okay? So there we go. And like if we could, we can even have a C ring here. If we wanted to, C, and then just place that appropriately, EP, EC. I probably shouldn't have done that way. An electron would have a larger electrical potential energy at C. That is actually true, EP, EC. And then here, just because I'm running out of space, EPEC. That's very poorly spaced, folks, and I apologize for that. Okay, so there you go. But what happens if, I wanted to move my electron from C over here to, D? Okay, well, what would happen there? Well, these represent, remember, equipotential lines. The difference in potential from C to D would be 0. So since the potential at C is equal to the potential at D, the difference in potential is 0. Therefore, the work done on an electron moving from those positions, from one position to the other, would be, in fact, 0, since that would go to 0. Oh, okay. Oh, hopefully what you're realizing is something really important from chemistry last year. Remember, the atom, your electrons orbit your nucleus, the positive thing in the center. Notice here, it requires no work to move along this. The fact that that's true is why matter is stable, folks. Because if it required work to go along the orbital, that would mean that you would either have to add energy or remove energy from the system in order to move along that path. That would not be a stable structure. So the fact that matter is stable is because these electrons are moving along these equipotential lines, which is kind of, I think, at least interesting. Okay. So there you go in terms of some ideas about this vocabulary. So I will admit some of this vocabulary sounds very, very similar to each other, but we have to understand that there are different definitions for these things that we have to learn to use with precision. So what vocabulary am I talking about? I'm talking about electrical potential energy is its own thing. Then we have electric potential. Then we have potential difference, which is also called voltage. And then we have potential gradient, which is something different as well. So we want to be able to use these ideas with precision in order to be able to explain what's going on. In the next video, we're going to talk about a critical experiment that was done at the beginning of the last century in order to figure out something about these particles that we know are the reason why objects are charged.